Hi everyone. So in today's video, we're going to be talking about the derivatives of logarithmic functions. And the structure of today's video is going to be actually pretty similar to yesterday in that we're going to be using implicit differentiation to find the derivative of f of x is equal to ln of x. So the reason that yesterday's video is kind of similar to today's video is that yesterday we were working with inverse trigonometric functions. And so we were able to kind of take advantage of the fact that, for example, inverse sine of x is the inverse of sine of x. And so similarly, logarithmic functions are inverses of exponential functions. And so because there's that relationship, that's what allows us to kind of rewrite the logarithmic functions a new way and use implicit differentiation. So we'll get there a little later. I first want to start by doing a quick review about logarithms. So I would recommend if as we go through this review, if you're like, I don't remember any of that, or if you feel like you never learned it or something like that, I would recommend looking at, I have some videos from 141, so that's pre-calculus 1 at North, from the end of last quarter that I'll put links to them in the description of this video. But if you feel like you need a little bit more review for logarithms, I would recommend checking those videos out that I will link. Okay, so the main thing we need to know is basically like the definition of a logarithm. So in general, the definition of a logarithm is that if log base b of a number x is equal to another number y, that is equivalent to I left a t off here, equivalent to saying that b, so the same number that was the base there, to the y is equal to x. So the way that I like to think about logarithms is that when you're evaluating a logarithm, it's basically asking you to find an exponent, right? Your answer for logarithms is an exponent. And specifically, it's the exponent that you need to use to go from here to here, right? Because if we look at the right-hand side over here, we're saying that whatever that answer is from your logarithm, that's that exponent that you would need to put on b in order to get x as your answer. So let's do just a few quick examples of evaluating logarithms. So for example, let's say that you were trying to take log base 2, I'm debating colors here, let's just use a different color. So log base 2 of 8. So what is log base 2 of 8? Well, log base 2 of 8 is equal to 3. And the reason for that is because 2 cubed is equal to 8. Or to do another slightly trickier example, so when we write ln, so let me write down the question first. So we're going to do ln of the square root of e. But what does ln mean? So ln is basically the same thing. It's kind of an abbreviation for saying log with a base of e. And so e we talked about when we talked about e to the x, so e is just a number. And so it's basically doing a logarithm, but instead of having your base being like 2 or 5 or some number like that, your base is e. So whenever you see ln, it's just a normal logarithm, but because it comes up so much, it has a special kind of abbreviation. So ln of e of the square root of e, well, basically this is asking us what exponent would we need to raise e to in order to get the square root of e. And so the answer is 1/2. Because if we take that base, so the base isn't written here, but if you wanted to, you could kind of put it in there. So that's the base. So e to the 1/2 would give you square root of e. Let's do one more. So let's say we took log. So I'll explain what it means when you just have log for a second, in a second, log of 1/10. So what is log? So if you write log without anything else, that means that you're using a log with a base of 10. So because log base 10 and log base e are both so important, that's why they both have kind of their own special name. So log of 1/10 would be asking us what power do we need to raise 10 to get 1/10? And so the answer would be -1, because 10 to the -1 is equal to 1/10. So that's basically what I want you to understand about logarithms, just being able to understand how they work and how to evaluate them. And then additionally, there's some logarithm rules that we're going to be making use of in a few places in this video. And I think I actually brought at least one of these up in a previous video, but let's review them again. And I'm not really going to explain like where these come from, so I would recommend, if you're curious, going back to the video that I'll link for a 141 video about this. And let me try to at least start out with straight writing. So logarithm rules. So logarithm rules are basically rules that allow us to simplify logarithms. So one example of a logarithm rule is that if you take log base b of x times y, so you're taking a logarithm of two numbers being multiplied together, that's the same thing as taking log base b of one of the numbers and then adding that to log base b of the other number. So as I said, I'm not going to really go into depth of where this comes from, but the general idea I would think about here is that what are logarithms doing? They're counting exponents, right? So like going back to this example, this is probably the easiest example to see it in. Where is this 3 coming from? It's coming from counting the exponent. Specifically, you're trying to figure out what's the exponent that I need to raise 2 to get 8. So because logarithms count exponents, if you take two numbers and multiply them together, that adds exponents, right? You know that there's an exponent rule that says if you multiply two numbers together, their exponents will add if they have the same base. So I'm kind of brushing over some details there, but that's kind of the general idea, is that multiplication inside the logarithm turns to addition because there's this exponent rule that says that multiplying turns the exponents into addition. So it's because logarithms are so closely related to exponents. So similarly, if you're taking a logarithm of two things being divided, then it's log base b of x minus log base b of y. And again, that's related to the rule that says that if you're dividing two things that have the same base, you can subtract their exponents. And then the last one is that if you're taking a logarithm of a number raised to another power, then you can bring that exponent down. I think this is the one that we mentioned in a previous video. You can bring that number down and multiply it with it instead. And that comes from the exponent rule that says if you take an exponent and raise it to another exponent, you can multiply the exponents. Okay, so we'll be making use of these logarithm rules a little bit later, because basically if you're taking the derivative of a function that is a logarithmic function, sometimes you can use these rules to simplify the function or kind of rewrite it a better way before you actually go in and take the derivative. And oftentimes that will save you a lot of time and complexity. Okay, so how are we going to do this? So basically, like I said, the main first goal that we're going to do here is we're going to use implicit differentiation to find the derivative of ln of x. So ln of x is going to be the logarithmic function that we're going to deal with the most. So f of x or y is equal to ln of x. We'll also talk about the derivative for like log base, 5 of x or other types of logarithms, but just in the same way that we learn the derivative of e to the x first, and we kind of see that function a lot more than like 3 to the x or 5 to the x. In a similar way, we're going to be seeing ln of x a lot more than any other type of logarithmic function. Okay, so we're going to do this very similar, like I said, to the last video. So if we have y is equal to ln of x, I want you to actually pause and I want you to think about how can you rewrite that statement as an exponential statement. So how could you kind of using the definition that we talked about on the previous page. So, oops, no. Using this definition here, how can you use that to rewrite ln y is equal to ln of x? So basically, if you have y is equal to ln of x, that is equivalent to e to the y is equal to x. Because whenever you're doing a logarithm, your answer of your logarithm, or kind of like the part on the other side of the equation, that's always your exponent. And then in this case, the base is e, and so that's why that e comes, where that e comes from. And then the input for your logarithm is the answer for the exponential. So what we're going to do is we're going to use implicit differentiation on the equation e to the y is equal to x. So what do we get when we do the derivative of e to the y using implicit differentiation? We get e to the y times y prime. And then what's the derivative of x? Well, that's just 1. And so as usual with implicit differentiation, we want to solve for y prime. So we get y prime is equal to 1 over e to the y. So that's true. Like right now we have a statement that is true, but just like in yesterday's video, because our original statement here was a function of x, we should also be able to write our derivative as a function of x. And in this case, it's going to be a lot easier than in yesterday's video, because the key that we have this time for translating between x and y is that e to the y is supposed to be equal to x. So here we have y prime is equal to 1 over e to the y. Well, that's going to be the same thing as x based on what we wrote down up above. I don't know why this line is there. Let me get rid of that. So we end up with y prime is equal to 1 over x. So very, very important derivative rule. And I should have mentioned in yesterday's video, the inverse trig functions, I mean, you definitely do want to know those, and they will come up in Calc 2 a little bit more than they come up in this class. But for sure, ln of x is one that you really want to know. So the derivative of ln of x is equal to 1 over x. So we can add that to our list of derivatives. So I'm not going to go through the same process for like log with a different base, but I'll just tell you what the rule is for that. So remember how with exponentials, so if you take the derivative of e to the x, that's just equal to e to the x, right? But if you take the derivative of a different number, let's say a to the x, that's equal to a to the x times ln of a. Right, so there's this kind of extra ln of a part hanging out. And so similarly with the derivative of, if you have, I'll say log base a of x, so it's going to be, instead of being 1 over x, it's 1 over x times ln of a. So it's kind of similar to what happens with a to the x. And if you go through the process of, like, if you just do the exact same process we did with a to the x instead of e to the x, you'll get the formula that we just came up with here in purple. So an example, just to kind of give a concrete example. So for example, if you were asked to find the derivative of, let's say, log base 2 of x, it would be 1 over x times ln of 2. So it's very similar to 1 over x, it's just kind of off by a factor of ln of 2. Okay, so the main thing I want to do for the rest of this video is a bunch of different examples using this new derivative rule we have together with the chain rule and some other rules. And something about ln of x, I mean, we'll see, it kind of works really nicely with the chain rule. So that's one of the main reasons that I want to look at it. So these are just going to be a bunch of examples of taking derivatives of ln of x, or ln of different things. Okay, so let's start with this one. So let's say our function is f of x is equal to ln of tangent of x. So this is going to be a chain rule problem, right? Because it's not just ln of x, it's ln of tangent of x. So our outer function is going to be ln of u, and our inner function is going to be tangent of x. So how does the chain rule work? Well, first we take our outer derivative. So that would be 1 over u, right? But then we want to put our original input back in. So we're going to get 1 over tangent of x. So that's a really, really important observation. I mean, it just comes straight from the chain rule, but I think it will kind of help you with these types of problems to just kind of realize that in general. So anytime you're taking a derivative of ln of something that's not just x, you're going to get 1 over whatever that thing is as part of your derivative. So that's the outer part of the derivative, is instead of being 1 over x, it's 1 over tangent of x, because that's our input in this composite function. So then we want to multiply that by the derivative of the inside function. So the derivative of tangent of x is secant squared of x. So that tells us that our derivative is secant squared of x over tangent of x. So this would be an example of a function that I would want you to know how to simplify. So basically, when you have, if you have two trig functions being like multiplied together or divided, you should always check to see whether it can be reduced in any way. So what do I mean by that? Well, secant squared of x can be written as 1 over cosine squared of x, right? Because secant is the reciprocal of cosine. And then tangent can be written as sine of x over cosine of x. And so if we were to simplify this, we would get, or rewrite this a different way, we would have 1 over cosine squared of x times cosine of x over sine of x. So dividing is the same as multiplying by the reciprocal. And so that simplifies to, so this square is going to go away, right? And this cosine cancels out. And so we're left with just 1 over cosine of x times sine of x, which maybe isn't like terribly simpler in this case. If you wanted to like rewrite this so that was just in terms of like singular trig functions, we could rewrite this as 1 over cosine of x times 1 over sine of x. And that's the same thing as secant of x times cosecant of x. So I'd say for most people, they would think this answer, this final answer we got here is preferable to what we started with here. And not to keep plugging my own videos, but I very recently, so just this week in 142, we were working on simplifying trig expressions. So if you want to check those videos out, you'll see there's a lot of examples kind of like what we just did here. Okay, so again, just to remind you, because we got caught up in all the trig stuff, but I just wanted to quickly point this out one more time. So when we're taking the derivative of ln of something, something that's not just x, I just want to really point out the format of our answer. So after we kind of put everything together, the original function ended up on the bottom, right? The original inside function. And that's just because of how the chain rule played out. And then the derivative of the inside function ended up on the top. So that's kind of if you want like a shortcut, you can just kind of remember that if you're taking the derivative of ln of something else, that original inside function will end up in the denominator. And then the derivative of that inside function will end up in the numerator. But you don't really have to remember that as like a separate fact because it's really just the chain rule. Okay, so I want to do a few more examples. So let's now do g of x is equal to the square root of ln of x. So in this case, we're also going to have to use the chain rule, right? But this time things are kind of flipped. So in this case, the ln is on the inside. So the outer function is going to be square root of u, and the inner function is ln of x. So when we take the outside derivative, so maybe let's rewrite this as ln of x to the 1/2. And really quickly, I just want to make one quick kind of, I just want to point something out. So what we have written here, you cannot use the power rule to bring this 1/2 down, or this rule. So this rule is very specifically only for when you have an exponent inside the input. So it is not true that if you have like log base b of x to the n, like that is not the same as n times log base b of x. So just pay attention to where that exponent is, whether it's on the input or whether it's on the function as a whole. So in this case, it's on the function as a whole. So the outside part of the derivative is going to be kind of doing the power rule on, but leaving ln of x as our input. So we're going to get 1/2 times ln of x to the negative 1/2. So that's the outer part of the derivative. And then we're going to multiply that with 1 over x, because that's the inside the derivative, right? Because the inside function is ln of x. So if we want to simplify this, so we can rewrite the first part as 1 over 2 times the square root of ln of x. And then we're multiplying that by the derivative of the inside, which is 1 over x. And so altogether, this simplifies to being 1 over 2x times the square root of ln of x. All right, so next I want to do an example that is going to be kind of similar. And this one we're actually going to do it two different ways, just to kind of show you that they both work. So let's say we had the function y is equal to ln of square root of x. So on a question like this, there's two different ways to approach it. One way is that we can use the chain rule like we did in the last example, but kind of flipping what our inside and outside functions are. The other way we can do this is, because square root of x can be written as x to the 1/2, we can use one of those logarithm rules to simplify. So let's do it both ways. So method 1 is going to be using the chain rule. So method 1 would be saying, okay, our inside function, or sorry, let me say maybe the outer function first. So the outer function is ln of u, and the inner function is square root of x, or x to the 1/2. So using the chain rule, our derivative would be, so the first part would be 1 over square root of x, right? Because the derivative of ln is 1 over x. So in this case, it would be 1 over u, and then the actual input is square root of x. So we end up with 1 over square root of x. So just like we said in that previous example, when you're doing the chain rule with ln of something, your original input always ends up in the denominator. And then we're going to multiply that with the derivative of the inside, which is square root of x. So the derivative of square root of x is 1 over 2 root x, or you could write it as 1/2 x to the negative 1/2. But I wrote it like this so that we could simplify more easily. So if we multiply these two things together, we'll get 1 over 2 times x, right? Because the square roots cancel each other out. So in this case, it's really not that bad to use the chain rule. That wasn't a lot of steps, but we'll see some examples in a little bit where this second method is going to make a big difference. But I just want to introduce it to you now on kind of a simpler example. So in this approach, we're going to use logarithm rules before we take the derivative. And that will basically make us not have to use the chain rule. So if our original function is square root of x, or ln of square root of x, that means that we can rewrite it as ln of x to the 1/2, right? We haven't taken any derivatives yet. We're just rewriting our square root of x as x to the 1/2. Then there's a logarithm rule. So the one that I was actually just talking about. So this one here. If you're taking a logarithm of x to a power, you're allowed to bring that power down out front. So in this case, it would be the same thing as 1/2 times ln of x. So our original function can also be written as y is equal to 1/2 times ln of x. And so now if we take the derivative, well, now we don't have to do the chain rule or anything. Now we can just do 1/2 times 1 over x. So we can just kind of use straightforward derivative rules. And if we multiply these together, we get 1 over 2x, which is exactly the same answer that we got on using the other method. So that's good. We should get the same answer both ways. Okay, so we're going to look at two more examples. So first one is going to be h of x is equal to ln of 5x times cosine of x squared. So I don't know about you, but I look at this and I'm not super looking forward to taking this derivative. So why not? Well, there's kind of a lot going on here. So first of all, we have ln, and we have ln of not just x, but something else. So we're going to have to definitely use the chain rule. Additionally, within that chain rule, we have a product. So we're going to have to use the product rule. Additionally, we have cosine of x squared. So we're going to have to use the chain rule again. So there's a lot going on here. You could definitely take the derivative just using derivative rules right away. But I personally think this is a lot easier if you first break this function up using logarithm rules. So in this case, we're going to use logarithm rules before differentiating. So in this case, so let me just go back to that list of logarithm rules to remind you. So if you're taking a logarithm of a product of two things, you're allowed to split it up as addition. And so in this case, we're taking a product of actually three things, right? We have 5 times x times cosine of x squared. And so we can actually split this into 3 parts. So we have ln of 5, we have ln of x, and we have ln of cosine of x squared. So ln of 5, and then that's as far as we can go. Let me actually maybe just point out one more thing. So you cannot bring this 2 down, and the reason you can't bring it down is because it's not, so if we had ln of cosine squared of x, well then the square would be on the cosine, and actually then you could bring it down. But in this case, the square is all the way inside of the cosine. You're not taking ln of something squared. You're taking ln of cosine, and it happens to be cosine of something squared. So the square is kind of too far embedded within for you to be able to apply that logarithm rule. Okay, so let's take the derivative. So first part, ln of 5. So ln of 5 is just a number, right? If you type it into a calculator, it'll tell you it's like probably somewhere between 1 and 2 would be my estimate of what ln of 5 is. It's a number. It's the number that you have to raise e2 to get 5. So yeah, so that's just a number. So the derivative is 0. So second part is ln of x. We just learned that the derivative of that is 1 over x. And then this last part, this one is a little tricky, because in this case, we're going to have to use the chain rule twice. So the first part of the chain rule, you always do 1 over your inner function, because it's, the derivative of ln is 1 over u, and so we end up with 1 over cosine of x squared. And I'm going to, in this case, use that kind of placeholder notation so that we can then kind of come back and figure out the inside derivative. So I'm just going to say times cosine of x squared prime, right? So we're taking the outer derivative here and then the inner derivative here. Okay, so we can get rid of this 0, so we have 1 over x plus 1 over cosine of x squared. And then what's the derivative of cosine of x squared? Well, we have to use the chain rule again, so now we're just focusing on this part. So the derivative of cosine of x squared is going to be negative sine of x squared, right? That's the outside part of the derivative, times 2x. That's the inside part of the derivative. And so putting this all together, we end up with 1 over x plus, and then we can move this into the numerator. So we have negative, and maybe let's just make this subtraction, minus sine of x squared times 2x divided by cosine of x squared. And then this can be simplified because sine of something over cosine of the same thing is equal to tangent of that same input. So we can rewrite this as 1 over x minus 2x times tangent of x squared. And that is our final answer. All right, one last example in today's video. So this is going to look very similar to the example we just did, but the approach is actually going to be pretty different. So let's say our original function is ln of now 5x plus cosine of x squared. So this one actually cannot be broken apart. So what's the difference? Well, in this example, we had a product, right? There was no addition. We were doing 5 times x times cosine of x squared. In this one, even though the 5 and the x are getting multiplied, overall, this is not a product, it's a sum. It's a sum of 5x and cosine of x squared. And going back to our logarithm rules, there's no rule telling you that a logarithm of two things being added up can be split up. And in fact, that is very much not true. I'll write it down here. It is not true that the logarithm of x plus y, that is never going to be equal to, or I shouldn't say never, maybe there's some numbers where it happens to be true, but in general, it is not equal to this. So unfortunately, there's really no simplification we can do in this case. So this one cannot be simplified using log rules. So instead, we need to just go straight to the chain rule. So like we saw in the other examples, so the outer function is ln, and so that means that the first part of the derivative is just going to be 1 over whatever the original inside function was. And then we want to multiply by the derivative of that inside function. So what's the derivative of the inside function going to be? Well, the first part of it, so the derivative of 5x, that's just equal to 5. And then cosine of x squared, well, we actually just did that, right? So we found that the derivative of cosine of x squared was this. So we can use the chain rule on that. So we have negative 2x times sine of x squared. So putting this all together, we get 5 minus 2x times sine of x squared divided by 5x plus cosine of x squared. So again, it has that kind of format that we saw in some of the earlier ones where the numerator is the derivative of the denominator. And that really just comes from the fact that of how the chain rule works. The fact that the chain rule puts our original input in the denominator and then the derivative of it ends up in the numerator. All right, so that is it for today. Today's worksheet has a bunch more practice with taking derivatives of different types of functions involving ln. And yeah, that is it. And I will see you next time.